Now we have learned the terms we use to describe motion. It can be nice to have some tools to help us to record motion so we can have data to use to describe motion more carefully. You can probably think of many different ways to record motion, especially because we have easy access to so much technology these days. We can use video recording or GPS for motion over long distances. But for this particular lesson, for starters, we'll be using something that is pretty low-tech. This thing here is called a ticker timer or a dot timer. And for this particular one, you can plug it into a wall outlet. And then when you plug it in, this motor here can be turned on, and then the motor is going to make this metal blade over here vibrate up and down. At the end of the blade, there's a pointy screw attached to it, which means that screw would tap up and down. This one here is a circular piece of carbon paper. Underneath the carbon paper, there's a paper tape, piece of paper tape going down. Let me plug it in. Okay, let me turn the switch on. See, it makes that sound. That's why some people call it a ticker timer. When it's on, this pointy screw will hit the carbon paper repeatedly. So, what do you think happens on that piece of paper? Yeah, you get dots. Of course, in this case, all the dots are at the same place. Since it makes dots, that's why we call it a dot timer. Now I want to use this dot timer to record the motion of this low friction cart rolling down this incline. How should I do it? Yep, I can attach the tape to the cart. Turn on the timer and release the cart. As the cart drags the tape with it, the dots on the tape would spread out. Now, think about the motion the cart went through. What do you expect the dots to look like on the tape? That's right. The dots on the tape should spread out, and they should spread out farther and farther apart as the cart picks up speed down the incline. Now, let's look more carefully at these dots and make some measurements. Now you can get a closer look at the dots on the tape, although they are kind of too light for you to see clearly. So I'm going to darken them for you. Now let's use these dots to describe the motion of the cart quantitatively. Since it is a one-dimensional motion, we can use an x-axis conveniently. Notice how I mark the dots every 4 spaces. 1, 2, 3, 4. 1, 2, 3, 4. The reason why I did not mark every dot is that the dot timer I used may have uneven time intervals between dots. By taking data every 4 intervals, I'm hoping to average out the unevenness. I begin the first dot over here because these dots come before it are really close together. Remember I turned on the timer before releasing the cart? So the first few dots overlap. The paper can also be curled at the beginning, so these ones may be caused by the paper tape getting straightened out by the cart. And then, of course, when the cart first started, it's very slow, so the dots naturally will be close together. So, in any case, I'm starting my measurements from this dot right here, which means that I can conveniently make it my origin. X equals to 0 right here. And then if I want the position for this one and these other ones, I'll just have to find their x coordinate, which means I need to find the distance to the origin. So if I make this measurement between the first dot origin and this one here, it will be about 1.3 centimeters. And then for the second one, I will also need to measure all the way to the origin because the x-coordinate is the distance to the origin. So for all of these, I have to go measure the distance to the origin. Okay, so I'm going to make those measurements. So now I have x equals to 0, and then this x equals to 1.3 centimeters, 3.6, 6.8, 11, and 16.1 centimeters. Of course, I also need the time. So I can say at the beginning, right here, t equals to 0. And then for this, it's 4 spaces. For that dot timer we used, it makes 60 dots every second. 60 dots every second means every time interval between the dots is 1/60th of a second. So 1, 2, 3, 4, 4 intervals means when this dot is made, the time will be 4/60th of a second. And that one, 8/60th of a second. And so on and so forth. So I label the time. I can ask you, say, what is the position of the cart at t equals to 16/60th of a second? Then you would measure the distance all the way to the origin, and that will give you 11 centimeters. I can ask you questions about average speed. Now in this case, the average speed and average velocity will be the same thing because the cart went straight, no zigzagging, no curving around. So the average speed will be kind of like average velocity, which means distance traveled and displacement will be the same. Let's say if I want to ask you to find the average speed, which is the distance traveled divided by the time from t equals to 4/60th of a second to 16/60th of a second. Then let's see, we'll need the distance traveled between this time and that. And that will mean it's 11 minus 1.3. Divided by the time, final time minus the initial time. That will be 16/60 minus 4/60. So that is 9.7 divided by 12/60, which means it's 9.7 times 60 divided by 12, 9.7 times 5. So this gives you 48.5. And what do you think the unit is? Since we used centimeters for the distance, seconds for the time, this is going to be centimeters per second. So that's the average speed. Average velocity will be the same amount. Now, of course, our distance, the standard unit is meters. But for this scale, centimeters is convenient. So it's perfectly fine to use centimeters. What if I ask you about instantaneous speed? So let's see. I can ask you, what is the instantaneous speed at t equals to, say, 12/60th of a second? Now remember, to find the instantaneous speed, you would have to do the average as well. But you'll have to take your average over a very short amount of time. So let's come here. If you want the average speed around here, the very short amount of time, you have a choice. You can measure the distance between 2 dots, 1 time interval. But since the speed is changing, it may be a good idea to do a little bit before and a little bit after. And if you want to consider about evening out the time because of the unevenness of the timer, You can go 2 dots before, 2 dots after, 3 before, 3 after, or 4 before, 4 after. Any of these will work. But basically, if you want the instantaneous speed, you want to take average over a short amount of time. Okay, so let's say if I choose to measure the distance between these 2 dots. I'll have to measure the distance and then divide it by the time interval. The distance between these 2 dots will be 3.7 centimeters. So this will be 3.7 centimeters divided by the time interval from here to here. Again, that will be 4 spaces. So it'll be 4/60th of a second. And if you do this calculation, you're going to get 55.5. And again, that will be centimeters per second. So that will be the instantaneous speed at 12/60th of a second, right over here. As in many fields, we can show people the data we have in numbers. We can also show our data in graphs for different effect. So let's plot a position versus time graph, which means a x versus t graph. Before actually plotting it, see if you can figure out what shape graph to expect by looking at how dots spread out. So you probably have figured out that once you plot the dots on the graph, in this case I have centimeters for the x-axis and times 1/60th of a second for the horizontal axis, the time. I get a curve that's curving up like this, not a straight line. Okay, because as you can see, the distance traveled by the cart gets bigger and bigger for the same time interval because the car speeds up as it goes down the incline. And that means that in the same time interval, the distance traveled between the interval gets bigger and bigger and bigger. In physics, we don't connect the dots, but we like to make a best fit curve. So I'm just going to very carefully draw a smooth curve that fits as many dots as possible. Okay, here's my best fit curve. And in this particular case, I happen to get a curve that's very smooth and fit the dots very well. Most of the time when you carry out an experiment, because you have errors, therefore the dots may not fit the smooth curve very well. You may have some dots that's higher, some dots are lower, but that's okay. Well, that's what we expect from experimental data. But in any case, physicists like to make smooth curve. We don't really like to have dots connected with straight lines. With this smooth curve, we'll be able to find the position of the object at different moments. For example, we can find the position at 16/60th of a second and then read it off the graph and figure out the x position. We can also find the position of the cart at 14/60th of a second. We can just read off the graph along that smooth curve we have. If we want the average velocity from a certain moment to another moment, of course we can do that too, because we can find the positions, find the change in position or the distance traveled. In this case, they're the same numbers, divided by the time. What if we want the velocity at a certain moment? For example, we want to find the velocity at t equals to 12/60th of a second. In that case, we'll have to do the same thing. For instantaneous velocity or instantaneous speed, what we want is the distance traveled divided by time, or displacement traveled divided by time for the instantaneous velocity, which means we'll still need to look at the distance traveled divided by the time. But we'll have to do that over a very short amount of time. So let's say a little bit before and a little bit after. So let's say we are looking at this little segment. A little bit before and a little bit after. A little bit before, its x position is here. A little bit after, its x position is right there. Which means your distance traveled, or the displacement, would be delta x. That is your delta x. And what is your delta t? This is your initial time. That is your final time. So this part is your delta t. Which means to find the instantaneous velocity at t equals to 12/60 of a second, we will have to find the distance traveled divided by the time for a very short amount of time. So in this case, it's the delta x over delta t. That means it's rise over run. So if I make a tangent line, a line that is tangent to my graph, this distance traveled divided by the time would be the rise over run, which is the slope of this line that's tangent to the x versus t graph. Instantaneous velocity would be the slope of this graph. So we can write it over here. The instantaneous velocity is the slope of the position versus time graph. Similarly, if we're talking about instantaneous acceleration, since it is an average delta v over delta t over a very short amount of time, that means this would be also the slope, but this will be the graph that is velocity versus time graph, because your delta v is the rise, the delta t would be the run. So the rise over run, delta v over delta t, that's the slope of the graph. If you are dividing, that is slope because it's rise over run, rise over run. Since the rise is delta v, the vertical axis is v. Since the run is delta t, the horizontal axis is the t. Now let's go over the last thing we need to add on this terms table. That is the displacement. Now according to this part, you can see that displacement is the average velocity times time. It is the average velocity times time. And it equals to something. Let's see. Let's look at this velocity versus time graph. And let's find the displacement corresponds to this motion. And this should be the average velocity times time. But the velocity keeps changing, so it's kind of hard to tell what the average velocity is. But we can do this. If we chop the time into little segments, say shorter amount of time delta t, then the velocity doesn't change so much. So we can say the average velocity is about this much. So this will be the average velocity. And then I multiply this by the time. That is height times the base, which gives you the area of this rectangle. So you can do all these different rectangles add all the areas together and you will get the total displacement for whatever time range you're looking at. Now, of course, this is not quite so accurate. To make it more accurate, what we can do is to chop the rectangles to thinner pieces. Then you get a better approximation. And then if you make it even thinner, it's getting even closer. Now, if you make them extremely thin, it's going to be pretty accurate. And that means when you make them extremely thin, the rectangles added together will give you the area under this curve. The area under the curve will be the displacement. So that's our last part. The displacement would equal to the area of a graph. It's the area of the velocity versus time graph. See, the area of a rectangle is the height times the base. This is the height, that's the base. When you are multiplying, that's referred to the area. And that's the height is the velocity, so the vertical axis is the velocity. The base is delta t, so the horizontal axis must be the time. So it's the height times the base. That's the area, that's the displacement. In our next video, we will practice solving some graph problems.